Hi everybody. For the next little while, I'm going to talk to you about the kinds of area questions you can expect on your final exam. But there's also a few similarity questions. I'd like to practice those with you too. I meant for these couple of sides to be parallel. AB is parallel to DE. In this figure, and we have these lengths given, you ought to make that sketch too. AB is 6, DE is 24. I think that little comparison is going to be important. As I look at these triangles, I know that these vertical angles are going to be congruent, and opposite those congruent angles, those are corresponding parts, aren't they? So the ratio is going to be 6 to 24 between these two similar triangles. Also, alternate interior angles are congruent, so this angle at A is going to match this angle at E. In fact, if somebody's going to make a similarity statement, it would look like this one. Triangle ABC is similar, and because angle A matched angle E, we begin that way. That would have gone to EDC, wouldn't it? And we may use that when we write proportions. See which side goes with which side. But first, ask me to find CE, but also I know that AC is 4. That length is 4. And who does AC correspond with? You would have to think that the angle at B is congruent with the angle at D. That would be true. Those are alternate interior angles, and opposite that angle, the side of 4 is opposite the angle, congruent angle, side CE. So that's the corresponding parts. Our triangles were similar in the ratio of 6 to 24. We're going to call that a ratio of 1 to 4. All the other sides are going to be in that same ratio. Let's work right at a proportion. AC came from the smaller triangle, and it was of length 4. So what about the side that corresponds to it, CE? Yeah, it'd have to be 16, wouldn't it? Just cross multiply. But this next one's a little more interesting. It tells me that I'm looking for BC as CD, this length and this length. And I know that BD is 25. It tells me that this full length is 25. But what are those two parts? I know they're going to add up to 25, but what else do I know for sure? That BC and CD are corresponding parts, and they're in a ratio of 1 to 4, aren't they? These triangles are in a ratio of 1 to 4, so the parts are in the ratio of 1 to 4. So these two lengths are in the ratio of 1 to 4. I could call them 1x and 4x, and they're going to add up to 25 plus each other, and they're adding up to 25. So we got really 5x there equals 25. That makes x equal to 5. So one of those sides must have been 5, and one of those sides must have been 4 times 5. That would have been 20. That makes sense to me. This could have been 5, and this could have been 20. That adds up to 25, and they're in that ratio of 1 to 4 that we needed. And this length was 16, so I think that worked out pretty cleanly. There's another little similarity idea right here. I think it's a lamp post and a guy standing in the light of the lamp post and looking at his shadow. The man is 6 feet tall, and his shadow is 12 feet long. He's standing 60 feet from the lamp post. How tall is that lamp post? And there's an easy place to make a mistake right here. You're going to write a proportion. I do see similar triangles. This triangle is going to be similar to the larger one. 6, the man's height is to the length of his shadow, 12. As the height of this pole, I'll call it x, I guess, is to the length of its shadow. But notice that's got to be 72, huh? A lot of people want to put that over 60, and that just won't fly. And then you cross multiply on this, and 6 times 72, I think we can do that. 12x will equal, and that'll be 420, and 12 more, 432. Divide both sides by 12. And let's see what this, really this is just a ratio of what must be 36, huh? Since this is a ratio of 1 to 2, that had to have been as well. So I think that that tower must have been 36 feet tall. Let's do the kind of area questions you got to worry about. I'm going to try to keep it small and work it on this page. I may need to make a sketch on another page from time to time. Given the perimeter of an equilateral triangle, find its area. And I don't want to do all 3 of these. Let me do one with 42 centimeters as the perimeter. Because it's equilateral, and all the 3 sides add up to 42, each one must be 14. I'm going to go ahead and drop an altitude on that guy. In an equilateral triangle, in any isosceles triangle, the altitude would bisect the base. This side was 14, so that part would have been 7. And I'm thinking what you're thinking too, that's going to be a 60-degree angle. So what about the length of that altitude? Yeah, and that 30, 60, 90 triangle, the short side times the square root of 3, huh? 7 root 3. So I'm going to get the area of that triangle right here, right now. I could go 1/2 times its base, 14, times its height, 7 root 3. And half of 14 is going to give me 7, times 7 is going to be 49 square roots of 3. I'll tell you what though, side squared square roots of 3 over 4 is a beautiful formula for the area of an equilateral triangle. And if had you done it with sides of length 14, it would have been 14 squared square roots of 3 over 4. That's 196 square roots of 3 over 4. That brings us back to that 49 square roots of 3. So that's a pretty good formula, side squared square roots of 3 over 4. Give the area of a rectangle with sides of these measured. Let me make that little sketch. A length of 3x minus 2 and a width of 2x plus 5. What would be that area? We're going to multiply them, aren't we? And I think we've been working with multiplying binomials throughout the year pretty much, squaring them and such. So this ought to be something you're used to. First term here times first term there, that'd be 6x squared, huh? The outside terms are going to give us a positive 15x. But the inside terms yield a negative 4x. Positive 15 and negative 4 can be a positive 11x in the middle. Write down more if you need to, and last times last is a negative 10. So I'd say the area of that rectangle would be 6x squared plus 11x minus 10. Give the area of a parallelogram with sides of length 7 and 12. I'm going to try one of those. That's supposed to be my parallelogram, not beautiful. I'll let this be 12, I'll let this be 7. And this angle could have been 30 or 45 or 60. I'm going to go with the 45, just see what flies there. But you know, in class we might want to try a 30 and a 60 as well. So there's my poor sketch. And I need an altitude. I need to remember that the area of a parallelogram is base times height. That's just a parallelogram is what I meant there. And no, that 7 is not a good height, but this would be a pretty good height right there. And that creates a 45, 45, 90 when we drop that altitude. And I got to find the length of that height. To go from the hypotenuse to the congruent sides in a 45, 45, 90, we got to divide by the square root of 2. So 7 divided by the square root of 2 ain't nothing nice, but we can't leave that square root of 2 in the denominator. Let's rationalize it. Square root of 2 over square root of 2. Multiplied by the number 1, we won't change the value, we'll just change its appearance. Giving me 7 square roots of 2 over a plain old 2. That would be the length of our height, or altitude. And then I got to go with base times height. That would be 12 times 7 square roots of 2 over 2. And because your final exam is multiple choice, you're going to have to recognize answers as they should be written. That 2 goes into that 12 6 times, and 6 times that 7, this is going to be 42 square roots of 2, huh? That would be the area of that parallelogram. And it would be good to try it with a 30 or a 60, but that's the general kind of question we're talking about. Given the perimeter, looking at the next one, given the perimeter of a rhombus and the length of a diagonal, find the area of the rhombus. I'm going to sketch a rhombus real quick. I think this deserves a little more space than that. A couple things I'm thinking about a rhombus. They're equilateral. The diagonals bisect each other, and the diagonals are perpendicular. So, knowing those kind of things, if the perimeter was 116, how big would the sides have to be? And that'd be 116 divided by 4, it's 29, isn't it? Yeah, 29 all the way around. And the longer diagonal, the shorter diagonal was 40. Okay, if this was 40, that must have been 20 and 20. And we're going to want to find this length, or that one, or both of them actually. We want to find the length of the other diagonal. Because the formula for the area of a rhombus is diagonal for a rhombus, diagonal sub 1 times diagonal sub 2 divided by 2. That's the area of a rhombus. Let's use it here. But first I got to find the length of this side. Let me call it x and hit it with the Pythagorean theorem. This is a triple, but not one you've heard 10 times. X squared plus 20 squared is equal to 29 squared. X squared plus 400 is equal to 841. Alexa, what's the square root of 841? X squared is equal to...
The square root of 841 is 29.
And so 29 squared must be that. Subtract 400 from both sides, and we got 441. take the square root of both sides, and yeah, x is equal to 21. That's an interesting Pythagorean triple, isn't it? 21, 20, 21, 29. So we got the length of the other diagonal. The other diagonal is 21 and 21, therefore 42. So now could you get the area? I say, yeah, I could. 40, that's a diagonal, times the other diagonal, 42 divided by 2. You could multiply first, but if you just take a half of one of those, that'd be 20 times 42, and that'd be probably 840. Yeah, I think that's so. Now you could find the area of these different triangles. I think the area of that triangle right there would be 1/2 times 20 times 21, that'd be 210, and 4 times 210 give you the same amount, wouldn't it? So pretty safe with that answer. Let's look at the next one, an isosceles trapezoid. I'll try to work it in that little space. I know I'm going to drop that altitude at either endpoint of the upper base. I see I'm creating a couple of 30, 60, 90 triangles there, the short side of which would have been 5 on both of those triangles. And that rectangle has opposite sides congruent, so that length would be 12. The altitude, yeah, the short side times the square root of 3. And that 30, 60, 90 triangle, 5 root 3. I think I can get the area of that trapezoid. Base 1, 12. Plus base 2, 22. Divide that by 2. Multiply by the altitude, 5 root 3. 34 divided by 2 be 17 times 5 root 3. 17 times 5 is 85. Square roots of 3. It'd be good to work at all the parts and add them up, but I'm not going to force you to watch me do that now. Let's work on this non-isosceles trapezoid. Still going to drop those altitudes though, aren't you? At either endpoint of the upper base. Got a 60 and a 30. The short side of this 30, 69 on the left is 6, and then the longer leg 6 root 3. Ooh, do we know any sides at all in this right triangle on the right? Yeah, I think we do, huh? The altitude is 6 root 3. That's consistent between these. So that length is 6 root 3. But that's the short side of this 30, 60, 90 triangle. You'd double it to get the hypotenuse if you wanted to. We just don't care about the hypotenuse this time. But how do I go from this short side, opposite the 30, to this longer leg, opposite the 60? Yeah, we're going to multiply by the square root of 3. 6 square roots of 3 times the square root of 3, that's going to give me 6 square roots of 9. That's going to give me 18. Yeah, to get from that short side to the longer leg, that 6 root 3 becomes 18. So, let's get the area of that one. It asks for the perimeter. We might go ahead and take care of that right now, I guess. I'm not going to worry about it. You could add them up if you wanted to. I see 30, 40, 50. I'll let you take care of that. Let's just get the area of it. Base 1, 20. Plus base 2, 44. Divided by 2. Times the altitude, 6 root 3. That looks like 64 divided by 2. That's 32. Times 6 root 3. And that'd be 192 square roots of 3. It'd be nice to check on all the parts if we had a lot of time, but I don't think we do. Given the length of the arc, give the length of an arc of a circle with a central angle of 135. Let that be 135. And a radius of 20. I'd have to remember that the circumference of a circle is given by 2 pi r. So the circumference of this circle would have been, with its radius of 20, 40 pi. And we're doing with a different angle if we choose to, but let me just do it with this 135. It will be that central angle 135 over 360. This angle over the full revolution times that circumference, which we knew to be 40 pi. And the trick here is that 135 3/60ths is the same as 3/8. Get a little bit crowded there. I can reduce that fraction of 135 3/60ths. That's 3/8 of 40 pi. That's 3/8 of the distance around this circle. And to do that quickly and easily, you could multiply first, but 8 goes into 45 times, and 5 times the 3 is going to give you 15 pi. And that would be the length of that arc. 15 pi. You could have done it with a 150-degree central angle, but what's really important there is when you put that 150 over 360, what happens with that fraction? 30 goes into both of them, huh? That'd be 5/12. 5/12 of whatever the circumference had been. Let's go and do a couple more things together. Each side of a regular hexagon has sides of length. It's 18. Give the area. I'm going to sketch a hexagon real quick. See if you could too. Not beautiful, but serviceable, I think. I know that a hexagon is made of 6 equilateral triangles. That's a real good thing to remember about a hexagon. I'm going to work on that equilateral triangle right there. This says that this thing has sides of length 18. This equilateral triangle has sides of length 18. I'm going to get an apothem, which is also the altitude of that equilateral triangle. Yeah, it's a 30, 60, 90. It's just like they are. This would have been a 9 in that altitude, or the apothem, 9 times the square root of 3. So we want the area of the hexagon. We can do that a couple ways. 1/2 times the perimeter times the apothem. That gives you the area of a regular polygon, any regular polygon. So 1/2 times, hey, what was the perimeter? 6 times 18 all the way around. 6 times 18, that'd be 108. Times 9 square roots of 3. And 1/2 of 108 is 54. Times 9 square roots of 3. And that'd be 450 and 36 more, so 486 square roots of 3. You can check me out. I might have made a mistake. So we got that one. But you might have said, hey man, what if I just found the area of that one triangle right there? 1/2 times its base, 18 times its height, 9 square roots of 3. That would have given you 81 square roots of 3. And if you multiplied that times 6, I think that would have given you 486 square roots of 3, huh? Yeah. So either way, those pretty good way to get the area of that hexagon. A rhombus formed by 2 equilateral triangles abutted. And that just means that they share a common side. We would like to get the length of those 2 diagonals, and then the area of the rhombus. This would be a rhombus if these are equilateral triangles. An equilateral parallelogram is a rhombus. But it asked me for the length of AC. Because these are equilateral triangles, this would have been a 30-degree angle. It's been a 60 that's been bisected. There's a 60. The hypotenuse is 18, so the short side would have been 9, and the longer leg would have been 9 times the square root of 3. These are congruent triangles, so this is also 9 root 3. So how about AC? I'm thinking it's 18 times the square root of 3. And this length 9 and that length 9 confirms that BD would have been 18, but that's nothing special because we knew that was an equilateral triangle. BD is just 18. Give the area of the rhombus, and then you're saying, well, that'd be easy enough. Diagonal 1, 18 root 3, times diagonal 2, 18, divided by 2. And pretty sure 18 times 18 is 324 square roots of 3 over 2. And that must be 162 square roots of 3. I think that's true. So each one of those must have been 40 and a half square roots of 3. One more thing for us to do. Let's take a look. A 30, 60, 90 triangle inscribed in a circle with a longer leg of length 12. That's a 30, 60, 90. That's a 12 right there. Huh? Now we're going to have to get to that short side pretty quick in this 30, 60, 90. And you got to remember to go from the long leg 12 to the short leg QR. We're going to have to divide by the square root of 3. Keeping that hidden from you. What does that become? Let's rationalize that denominator, square root of 3 over square root of 3. Yeah, it's going to give me 12 root 3 over 3. So 4 square roots of 3. That would be the length of the short side, which is also the radius, isn't it? Because when I double that to get the hypotenuse, that's the diameter. So I know the diameter is 4 root 3. But so we should remember that the radius is 4 root 3. We want the area inside the circle, but outside the triangle. Let's get the area of those two things. What would be the area of that circle? Pi times the radius squared, and we figure the radius, I figure the radius is 4 root 3. Squaring, that's kind of an interesting little task until you get used to it. We got to square the 4, that gives us a 16, and the square root of 3, that gives us a full-on 3. So that's going to be 16 times 3, that's going to be 48 pi. That's the area of that circle. But now what about the area of that triangle? Yeah, 1/2 times the base times the height would work pretty well, huh? You could let that 4 root 3 be the base. And the height, the guy that's perpendicular to it, that 12. And that would give me A half of 4 is going to give me 2 times 12, therefore 24 square roots of 3. The shaded zone, my friend.